Drowsy driving is a major public safety issue and continues to cause thousands of injuries and deaths every year. Recent analyses from 2017 to 2021 show that about 17.6% of all fatal crashes involved a drowsy driver, which means almost 30,000 fatalities over just a 5-year period. What makes drowsy driving particularly dangerous is that drivers often don't realize when they're becoming fatigued, and drowsiness builds up gradually and goes unnoticed until it is already too late. This makes early detection incredibly important, especially in real time before a dangerous situation develops. Another important point is that people are actually very poor at judging their own alertness. Many assume they're fine to drive, even when their reaction speed and attention are already impaired. Younger drivers, especially those from the ages of 16 to 20, and male drivers have shown the highest rates of drowsy driving crashes. The environment also plays a big role. Nighttime driving, long monotonous trips, or low lighting conditions all significantly increase the likelihood of fatigue. So we have a situation where drivers can't reliably self-assess the conditions, and that often works against them and results in fatalities and crashes. This clearly shows that automated drowsiness monitoring systems would be very helpful for drivers. Our project focuses specifically on eye state detection, which means determining whether someone's eyes are open or closed from a single image. The reason we chose this approach is that eye behavior is one of the strongest biological markers of fatigue. As a driver becomes drowsy, their eyes tend to close for longer periods and their blink rate changes in very predictable ways. For example, prolonged closure or an abnormal blinking frequency can indicate early signs of microsleep. Another advantage of doing this is that modern cameras allow us to do this in a way that is non-invasive and real-time. Unlike physiological sensors, which can be uncomfortable or require physical contact, a simple camera-based system can continuously monitor alertness without having to distract the driver. So eye state classification becomes the foundation for more advanced drowsiness monitoring, and that is a task our project is aiming to solve. The goal of our project is to build a deep learning system that can accurately classify whether a person's eyes are open or closed from a single image. To do this, we worked with the MRLI dataset, which contains more than 85,000 labeled images that have various kinds of conditions under which pictures were taken, like different lighting conditions, different camera angles, and different subject appearances. We implemented two different models, a simple convolutional neural network, which serves as a baseline, and a pre-trained MobileNetV3-Large model, which uses transfer learning to extract more powerful features. Our aim is to evaluate how these models perform under a realistic subject-wise split, where the model is tested on people it's never seen before. We want to determine which architecture is more reliable for a real-time drowsiness detection system that could be deployed in modern vehicles.
Hi everybody, my name is Mosef and I'm gonna talk about the dataset we use here in our project. Dataset is called the MRLI. It is a large-scale eye image dataset designed for driver drowsiness detections. It contains approximately 85,000 images of eyes captured under diverse real-world conditions with 37 unique subjects. Each sample is labeled 0 for open eyes and 1 for closed eyes. For the data split, uh, we have to avoid data leakage, so images from the same person must not appear in both training and testing. Therefore, the split is done by subject folder, so it is a subject-wise splitting here, not by individual images or a random split. Uh, it ends up with 70% of subject in training and 10% of subject in validation and 20% of subject in testing phase. To pre-process these images, which are like raw images varying in size between 70 and 150 pixels. Every image is resized to 128 by 128 to match the CNN required input shape. We use also a data augmentation here to increase generalization and reduces overfitting. This augmentation, it is just in training phase, so we cannot use this in validation or testing here. The two operation we use here is a random rotations, which simulate natural head tilts while driving. We use a rotation of 50 plus or minus 15 degrees, and also an horizontal flips, which help generalize across left, right eye images. We implemented two models in our project. The model number one, which is a simple CNN, it has two convolution layers followed by a small classifier. The first layer is, it has like 16 filters. It detects basically eye features such as edges and contours. The second one with 32 filters, it learns more detailed patterns like eyelid shape, iris boundary, and closing patterns. We At the end we had a fully connected neural network to classify this in two classes: so open eyes and closed eyes. The second one, which is like a more powerful model, it's called the MobileNetV3-Large. It is a family of neural networks designed for efficient inference on mobile and embedded devices. The original MobileNet version 1 introduced a technique called depthwise separable convolutions, which drastically reduced the number of computations compared to traditional convolutions. So they are particularly well suited for tasks like image classification, object detection, and semantic segmentation on devices with limited computational power. Our training configuration is an Adam optimizer, 0.001 learning rate, which is small, a cross entropy loss function, and 10 epochs with 64 batch size. We run this code on a free T4 GPU on Google Colab. So I'll let my friend here to present the results we get.
Now that we've discussed the dataset and methodology, we'll go through the results of our experiments. We'll compare the baseline CNN with the pre-trained MobileNet V3 large model using accuracy, precision, recall, F1 scores, and also confusion matrices. These results come from a subject-wise test set containing over 21,000 images from 8 individuals the models never saw during training. So starting with accuracy, the difference in the models is quite clear. Our CNN model achieved about an 84% accuracy, which is quite decent considering the dataset's difficulty and that there's a lot of variation in the lighting, poses, and obstructions in the images. But the MobileNet model used pre-trained ImageNet weights and reached an accuracy of 97.58% on the same test set. This improvement really shows how important and effective transfer learning is for eye state classification, and MobileNet's pre-trained features allow it to generalize much better, especially when dealing with subjects that the model has never encountered before. So the precision, recall, and F1 scores for both models, and we'll start with the CNN, where the CNN achieves 93.8% in precision, whereas the MobileNet achieves 98.1%. This shows that the MobileNet is far better at avoiding false positives, and it rarely predicts closed eyes when the eyes are actually open. Next, we move on to recall, where we see the largest difference. And the recall is very important for safety because recall tells us how well the model detects actual closed eyes. The CNN's recall is only about 79.8%, meaning it misses a lot of closed eye cases, whereas the MobileNet achieves a recall of 97.98%, which means it almost never misses true signs of drowsiness. Finally, the F1 score, and this balances both the precision and recall, and it also shows the same pattern. The F1 score for the CNN model is 86.25%, whereas for the MobileNet model it's 98.06%. So across all three models, we can see that MobileNet showed a much stronger performance, especially for detecting the dangerous cases where the eyes are closed. So now we look at the confusion matrices, and we can see which model performed better on the test set. On the left, we have the MobileNet V3 large model, where the diagonal dominates the plot, meaning nearly all predictions are correct. Out of more than 21,000 test images, it misclassified only 248 closed-eyed images and 269 open-eye images as closed. These numbers are very small relative to the class sizes, showing a very strong reliability. On the right is the CNN confusion matrix, and here we start to see the weaknesses of the baseline model. The CNN produced 700 false negatives, meaning it predicted open when the driver's eyes were actually closed, and this is the most dangerous type of mistake in a drowsiness detection system. It also produced 2,697 false positives, which create a lot of unnecessary alerts when deployed, and this can be very, very annoying for a driver. Another difference is the distribution of colors. MobileNet's heat map shows a strong distinction between the classes, meaning it understood better, and the CNN's matrix looks more mixed, indicating that it struggles to properly separate open and closed eyes. Overall, these confusion matrices clearly illustrate why MobileNet v3 is much more suitable for real-world deployment, and it makes far fewer dangerous errors and handles the subject-wise variability much better. Okay, next we move on to performance analysis. So based on the results we've seen so far, we can see how this MobileNet model performed better than the CNN. The CNN produced a very high number of false negatives, meaning it often predicted open eyes when the drivers were actually closed. This makes the CNN unreliable for any real drowsiness detection systems, because missing closed eyes is the most dangerous type of errors. You never want to do that. So evidently transfer learning made a huge difference. The MobileNet v3-Large model, which used pre-trained ImageNet features, learned a lot more patterns from the exact same data. That's why we see big improvements not just in accuracy, but especially in recall and the F1 scores. So these metrics show how the model's ability to detect real signs of drowsiness. And MobileNet also showed very stable performance over the training epochs and generalized extremely well to completely unseen subjects. Even though the test set consisted of individuals the model never saw during training, MobileNet still maintained a very high accuracy and very low error counts, which is really good. This level of accuracy is very important for real-world deployment because it has the potential to save people's lives. So practical implications is that the high recall in this case is very critical because in a safety system like this, missing a closed eye, even briefly, could mean failing to detect early signs of drowsiness, and this is the worst kind of error that could happen and could cause more fatalities and crashes. MobileNet's recall of nearly 98% makes it much more trustworthy for continuous driver monitoring. MobileNet also produces far fewer false positives, and this matters because too many unnecessary alerts would annoy drivers and reduce the system's credibility. A practical monitoring system needs to have a balance where it should be sensitive enough to detect drowsiness, but not disruptive. MobileNet v3-Large is designed to be fast and lightweight, and even though it performed much better than the CNN, it is still efficient enough to run on embedded hardware like in-car cameras or edge devices. This makes it a viable option for integration into modern vehicles where computational resources can be limited.
As a conclusion, we can say that MobileNet v3-Large significantly outperformed the CNN across all metrics. It achieved 97.58% accuracy and had good precision, recall, and F1 scores. The CNN baseline lacks the feature capacity needed for real-world variability. As the feature works, we can evaluate performance on real driving footage or in-car camera systems. Also deploy the model on embedded hardware like a Raspberry Pi or Jetson Nano to test real-time performance. And finally, we can explore lighter architecture like the MobileNet v3 Small or efficient net light for low-power vehicle systems. As limitations, currently the model only classifies single images and doesn't analyze temporal patterns such as blink duration, which can be detected here like in real-time video recording, so real-time video cameras. Performance could vary under extreme lighting conditions, camera motion, or partial face covering. Thanks you